All right, today's topic is enzymes. We'll begin with a definition. That is a protein catalyst that speeds up a reaction. Now, it does this by lowering the activation energy. I don't know if you guys remember that, but there was a diagram showing the energy required to move a reaction forward with so this is what the reaction looks like. There's a certain amount of energy that must be overcome before the reaction will proceed. So this would be with an enzyme. This activation energy, which is the highest point right here, is relatively low. But without the enzyme, it would be much higher. There'd be a bigger mountain to be overcome. That would be without the enzyme. So you can see that when the enzyme is present, the activation energy is lowered, and that has the effect of speeding up the reaction. Now, just another note, enzymes, the names of enzymes usually end with ACE. So some examples would be like catalase. That's going to be the enzyme that we look at in our next lab. Helicase is an enzyme utilized in DNA replication. And the list goes on and on and on. Amylase, catalase, topoisomerase. There's just so many different enzymes involved in the different reactions. So when you see that the name ending in ACE, you know it's referring to an enzyme. Also recall that there's a lock and key fit, and that if the shape of the lock is altered, then you're not going to get a reaction. So what we're going to experiment with in our lab is we're going to try to change the shape. We're going to try to, using heat, we're going to try to change the shape of the enzyme, and we'll detect if that took place by kind of assessing how much it's reacting. So we'll see that if we change the shape, if it still reacts or not. So anyways, just the general picture is that you've got the enzyme. The enzyme has a specific shape to it, and this would be the lock and key fit that we're referring to. So this here is the catalase, let's say, and then the substrate is the thing that's reacting. So this here is the substrate. And in the case of our lab that we'll be investigating, our substrate will be hydrogen peroxide. So the hydrogen peroxide will connect to the catalase. It'll form a enzyme substrate complex where it's actually connected, right? And once it connects, there's a kind of a reaction that takes place, and that's going to yield some products. So what it'll do is it'll actually break down the hydrogen peroxide into its products, and then the enzyme is ready to go and do it again. The enzyme can be reused, and a new molecule can come in and react again, and the process just repeats until all of the substrate has been reacted. So in the case of this catalase reaction that we will see tomorrow, you got the enzyme, right? We usually write the name of the enzyme over the arrow, and then we have to indicate what the products are. So in this case, the decomposition of hydrogen peroxide will yield a water molecule, and then this oxygen gas that is going to be visible to us. We're going to capture that gas and measure it. One of the other products is energy in the form of heat. You'll notice that when this reaction takes place, the little flask feels warm to the touch. And that's because this is an example of one of those reactions that where you are, I guess you could say, increasing entropy, right? We're breaking molecules apart. Okay, so yeah, so that's good. So that's the basics of enzymes. This is our specific reaction that we're going to conduct tomorrow. So let's talk about factors that can affect the enzymes themselves. What are some ways in which we can alter the shape, the lock and key fit? Well, before we talk about those factors, I do want to just quickly discuss a general trend in the concentrations. So there's two things we can monitor the concentrations of. One would be the substrate, that is the hydrogen peroxide, and then the other is the product. So we got substrate here, and then the product is oxygen. So what we might be curious to look at is how are those concentrations changing over time? Now, at the beginning, before any hydrogen peroxide is reacted, we would expect the hydrogen peroxide to be concentration to be high. But as time goes on, as the reaction proceeds, we expect that hydrogen peroxide concentration to decline. And we expect it to decline rapidly at first, and then it kind of starts to slow down as its concentration decreases, the number of collisions decreases. And if the reaction is thorough, it may actually go all the way down to zero. In other words, every molecule of hydrogen peroxide will have reacted. Now, what's happening to the concentrations of the oxygen? That's the product. Do we have any product at the beginning? No. So we're going to start down here with zero product. However, as the reaction proceeds, more and more product is produced. And in fact, the product is produced most rapidly at the beginning, and then it starts to taper off where no more product is produced. So we got product here and substrate here. Now, what is, in this particular case, what is the product? As we said, it is oxygen gas. So notice, students, that the rate of change in the concentration is the steepest at the beginning. And then it's the least steep at the end. In fact, the rate of change is zero at the end. It's no longer changing, it's just leveled off. The reaction is done. Okay? So that should be what we see tomorrow. We should see the reaction being most violent at the beginning. And that's because the concentrations are the highest, and so the collisions are taking place at a higher frequency at the beginning. So let's now talk about those factors. We mentioned that there are some factors that affect the rate of the enzyme reaction. So we're just going to list those. Rate of reaction, 5 factors. Okay, so number 1 is the pH. Number 2 is the temperature. Number 3, substrate concentration. That is, how many molecules are there per unit of area. 4 would be the presence or absence of inhibitors. And then lastly would be the enzyme concentration. How much of the enzyme do we have? So those 5 factors will affect. So let's talk specifically now about pH. If you look at the rate and you compare the rate to different pHs, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, on a scale of pHs. So to do this experiment, it would be quite difficult, actually. You'd have to do 10 different experiments at different pHs, and then you'd have to analyze the rate of the reaction at each of those pHs. And for most enzymes, their highest rate of reaction is usually in the neutral pHs. And then as you get to the more extreme pHs, the rates go down. So like if I asked you, what is the rate of reaction at pH 3? You would go, okay, 1, 2, 3. And then you would come over here to figure out what the rate is. If I asked you what's the rate of the reaction at pH 7, you'd say, well, that's the highest that it ever is. That's the peak. And at the extremes, the reaction might actually be as low as 0. Because at those extreme pHs, the enzyme denatures, and so the shape changes. And the shape might change so dramatically that there can no longer be a fit with the substrate. So there will just be no reaction. Now, why does the shape change? The extreme pH alters the bonding of the R groups in the protein. You remember the R group interactions. Well, if we go to extreme pHs, the presence or absence of protons will alter the way that those connect. So it has an effect on the shape. So in this case, this is the optimal. Now, it's not always at pH 7. For example, there are enzymes in the lysosome that have an optimal rate of reactivity at a lower pH. They're designed to work that way. So it really depends on the enzyme. Okay, but what about temperature? So with temperature, you see a similar pattern. If we have like freezing temperatures and then we have like boiling hot temperatures, we will typically, for most enzymes function nicely somewhere in this area here. Usually somewhere in this area here, like 20 Celsius. At 0, we're not going to have any rate of reaction, but as it gets warmer, we might start to see some reaction. It'll probably reach its peak around 20 because that's body temperature. And then you get too much hotter than that, and it's going to decrease down to 0. You get to boiling, and the enzymes will have warped and changed shape too dramatically. So you could say maybe here at this point, the high temperatures begin to denature the enzyme. Now, why is the rate of reaction so low in here? This is due to cold temperatures. So the cold temps slow the frequency of collisions. It doesn't have as much to do with the shape of the enzyme as much as it is just the movement. There's just not a lot of molecular movement when you're at those low temperatures. Okay, so that's good there. So generally, right in here, we can comment. We see as temperatures increase, in this local area here, like between 0 and 10, let's say, we see an increase in the rate of reaction. Rate of reaction also increases. Now, the reason for this is, as I said, due to increased molecular motion, right? I don't know if you guys are familiar with the concept of temperature, but as a solution increases in temperature, the molecules move faster, they move around more. So we get increased molecular motion, which increases the chances, or you could say frequency of collisions between the substrate and the enzyme. So the enzyme and the substrate, they have to connect with each other, and they only do so randomly. There's just picture them as zipping all around and bumping into each other. And the faster they're moving, the more likely they are to bump into each other and react. So that's kind of the reason for this trend, that this general trend of increasing temperature increases the rate of reaction. Okay, so next we'll look at the substrate concentration. Now for this particular factor, this would be like if you had a really high concentration of the reactant. So a high concentration of hydrogen peroxide, let's say. Generally speaking, as that concentration increases, so you could test out different concentrations, like low concentrations, really highly concentrated solutions. And as you increase those concentrations, the rate of this reaction will increase, but only up to a certain point. And it's at this point the active sites become saturated. So what this means is increasing the substrate no longer has an effect. Now, why would that be? I like to do this funny analogy of, like, let's say that we had a student, right? The student is the enzyme. The student is tasked, student represents the enzyme, right? And their function is to unwrap starbursts. That's the reaction that they're responsible for doing. And let's say that generally it takes the student about 1 second to unwrap it. If I'm dishing out a starburst to that student once every 30 seconds, they can easily react and unwrap the starburst, right? So if I start giving them starbursts faster, they're going to be able to perform more reactions. But if I dump an entire bucket of starbursts in front of them, that's not going to help the reaction go any faster. In other words, at this point, the rate of the at this point, right? Once I've dumped a whole pile of starbursts in front of them, the rate of the reaction no longer depends on the starburst, the concentration of starburst, but it depends on how fast the student can unwrap the starburst. So we're going to say at this point it depends not on starburst concentration, but on how fast the student can unwrap. Okay, so that's my funny analogy, and that's referring to this point right here, right? At this point, I've dumped a whole bucket of starburst, and me dumping a second bucket of starburst is not going to help, right? The student is saturated with starburst, and adding more starburst does not increase, and so that's why we get this leveling off, right? Early on, early on it did help because I was giving so few starbursts that increasing how much concentration I gave did have effect early on. But at a certain point, you just can't work any faster. The active sites are saturated, and we no longer see an increase in the rates. Okay, now what about enzyme concentration? So, like in this case, the number of students that I have unwrapping the starbursts. Well, in that case, if I increase the number of students, I should see that should always help. The number of people that can unwrap these starbursts. If I increase the number of students unwrapping, I should always see an increase in the rate. In other words, there is no point at which it levels off. Okay, so you can see the difference there between those two factors. One of them levels off, the other does not. And I hope that my starburst analogy helps make sense of those trends. Okay, so lastly is this idea of inhibitors. So inhibitors are molecules other than substrates that bind to the enzyme active site. So obviously, if some other molecule jumps in there and blocks it, that's going to decrease its rate of reaction with the substrate. So they can either, the binding can be permanent or temporary blockage, right? These inhibitors will block, and it can be temporary or permanent. It can be competitive, which means that it's attaches to active site, or it can be non-competitive, where it's binding to another spot. Like, in other words, it binds to an allosteric site. Allosteric just means that it's not the active site, it's some other part of the enzyme. But by binding to that allosteric site, it alters the shape and therefore prevents the reaction. All right, I think that sums it up. We'll go ahead and end.